Welcome to the Foundry by Forge College. So, in today's explainer, we are tackling a seriously massive topic in our blockchain fundamentals track, signature verification. Now, if you've been following along, we're picking up right where we left off after learning how digital signatures are actually created in our foundations lesson. But creating a signature, that's really only half the battle. The real question is, how do we actually prove to a skeptical system that it's legit?
Well, here is our blueprint for today. We're going to look at the verification pipeline, normalization and hashing, cryptographic consistency, freshness and replay, common failures, and finally, wrap it all up. Let's just dive right in, shall we?
All right, Section 1, the verification pipeline. Think of this as your deterministic security scanner. See, verification isn't just some magical yes or no button. It's more like a notoriously strict bouncer at an exclusive club. If you don't meet every single criteria in the exact right order, you're bouncing right off that velvet rope. Here is how this three-stage filter actually works. First, we check the raw bytes. Second, we evaluate the complex cryptography. And third, we do a final check on the timing. Each step is specifically designed to catch a totally different flavor of disaster.
Moving to Section 2, normalization and hashing. The big question here is, were these exact bytes signed?
This first filter asks a simple but absolutely crucial question. Enter canonicalization. I know, it sounds like an intimidating piece of jargon, right? But honestly, it just means forcing everyone to speak the exact same dialect before hashing. It organizes the data into a universally agreed-upon format so there are literally zero misunderstandings.
Because think about it. If the sender and receiver disagree on even a single invisible space character, the whole process falls apart right here. Once canonicalized, the verifier computes their own fixed-size digest from this normalized message using a hash algorithm like SHA-256. And here's the kicker. It has to match the signer's digest byte for byte. If there is a single bit out of place, the machine spits it out immediately, absolutely no exceptions.
Okay, Section 3, cryptographic consistency. Basically, did they use the right key? So, if your bytes match perfectly, congratulations, you've survived round 1. Now you face the cryptography. This step checks the algorithmic invariant. Now, that's just a very fancy, math-heavy way of proving the signature actually matches the digest under the provided public key. In plain English, it proves the sender actually held the correct private key and didn't just casually guess it.
But here's a fun fact. When the math fails here, surprisingly, it is rarely some master hacker in a hoodie trying to break into the network. It's usually just a mundane typo. A bit flipped during transmission, someone confusing DER encoding with raw bytes, or a dev just using the wrong curve parameters. Up next, Section 4, freshness and replay. Is this ticket still valid today? A lot of developers think the cryptography is the finish line. It's not. This brings up a critical question for anyone building in Web3. If the math is perfect and the signature is 100% cryptographically valid, do we automatically let the message through? The answer to that is a resounding no. Just like checking the expiration date on a questionable carton of milk, we absolutely must verify timestamps and nonces. Those numbers used only once. Without these freshness rules, a malicious actor could just grab a perfectly valid signature from last year and replay it today to completely drain a wallet. Not good. Which brings us to Section 5, common failure modes. Let's inspect the rejection bin. Look, if our security scanner goes beep and rejects the signature, don't panic. It happens to the best of us. Those opaque error codes actually translate into easily fixable problems. Got a digest mismatch? Well, you've got an encoding issue. Invalid signature? Your keys are wrong or the data got corrupted. A format error simply means parsing problems. And a replay error? That means your math is actually perfect, but your ticket is just expired. Honestly, knowing how to read these will save you hours of aimless, tear-filled debugging. Finally, Section 6, wrapping up and securing the blockchain. Let's step back and look at the meticulous blueprint we've just survived. If there is a golden rule to remember from this entire explainer, it is this. Mathematical verification is totally useless without protocol-level freshness checks. I mean it. You can have the most unbreakable cryptography in the world, but if you accept yesterday's ticket today, your system is still compromised. So what's next? Well, in our next lesson, we are going to take this pipeline and learn how to embed these verified signatures directly into actual blockchain transaction flows. We'll see how all this theory secures real-world networks. Thanks for exploring this security blueprint with me. To master more Web3 fundamentals and dive deeper into cryptographic hashing, definitely head over to forge.college. But before you go, I want you to ask yourself this. If a single flipped bit or an outdated timestamp can invalidate a $1 million transaction, how foolproof is the code you are writing today? Keep building, keep learning, and I will see you in the next explainer.